As we continue our discussion about input-output port space, you can have in the input-output address space combinations of 8-bit ports, 16-bit ports, or 32-bit ports of the physical devices. And these are really physical input-output address space. There is no any kind of virtualization of this address space. So only the operating system can access these physical addresses in input-output address space. So a really simplified block diagram for Neumann architecture computer. You have the CPU, you have the system bus, which of course includes addresses, the data bus, and the control lines, and everything is synchronized by the finite state machine inside the CPU in terms of the statuses of input-output ports for devices and enabling reading and writing of memory. So if you think about an arithmetic expression such as negative a plus b multiplied by c, in terms of for Neumann Computer Model, program is a sequence of instructions, and each instruction has a unique binary code or binary encoding, and that includes both the code of operation and the code of operands. So these A, B, and C have to be presented to the CPU in terms of recognizable operands. So this could be then potentially written as a series of machine instructions using IBM PC assembly syntax. So you can see that variables A, B, and C represented by CPU register AX, BX, and CX. And here we try to use examples of instructions that would be able to negate value in X, multiply BX by CX, and store the result again in register BX, and then add AX and BX. So arguably, using these registers is similar to using some sort of variables or values somewhere in memory A, B, and C. So these are examples of instructions with their unique mnemonics of operations and the set of operands that they actually operate on. So the instructions, like each single one of these in our example, are the most basic units of processing. So they're atomic, they're loaded into the CPU as one single unit, processed as a single unit, and they have predictable sort of like inputs and outputs in terms of what they manipulate. And of course, control unit, which is a finite state machine, controls all the steps in executing individual instructions and then advancing to the next instruction. So each instruction has its own unique address, and the control unit knows where the address of the next instruction is, because it knows that program is a sequence of instructions in computer memory. So instruction components, as we already underlined, unique codes of instruction. It could have one operand or two operands. So, and in case of two operands, for instance, this example of move from source to destination. So this is like the source of the value, and this is the destination for moving value from one place to another. And the direction is just like in the assignment, from right to left. So in our course, we're going to study Intel x86 instruction set architecture, and instruction set architecture, of course, means a combination of all instructions available on the specific platform. And it's pretty popular, so it allows to get familiar with Microsoft Microassembler, use various debugging tools, try to explore a little bit more the possibilities of using assembly code mixed with C and C++ programs using Microsoft Visual Studio, and other topics like arithmetic instructions, addressing modes, ways to access memory, and ways to invoke different subroutines, including mixed mode programming. For instance, C or C++ program invoking a subroutine written in assembler, and vice versa. So this is quite interesting range of topics that we're going to talk about in our course. The highlights of instruction set design on a specific CPU, and by the way, x86 refers to 32-bit version of Intel architecture. So the instruction set architecture is an important design issue for CPU designers. That's one part of one highlight, that it can support other facilities in the system, but generally it's difficult to redo the instructions, change their codes, because there is a tremendous pressure to keep support for prior versions of software. Even in 64-bit world, there is a significant effort to allow prior versions of 32-bit programs to continue to run on the 64-bit platform. And in general, we can refer to it as a legacy support, is the opposite of expandability, which is the looking into the future, and we want to be able to accommodate new instructions, like build and design new instructions while supporting the older instructions. Each instruction requires some number of transistors, of course, in the CPU silicon die. So here, again, we discuss this set of idea of the instruction formats. So generally speaking, you have the operation code, which is unique code represented in assembly by some sort of mnemonic, that's cryptic version of the word move in our case, and a couple of operands right here. So we have unique opcodes, and when the instruction is loaded from memory into instruction register, there is an instruction decoder. Of course, it's like a demultiplexer, which decodes the instruction and activates certain line, which activates the circuitry specific to that set of transistors responsible for execution of that specific instruction. So the rest of this presentation is actually covering some history of IBM PC assembly and IBM PC architecture. So I'd encourage you to read the rest of this presentation as a self-learning exercise.